Hello and welcome. In this video, we are going to go over combustion in open steady reactors. Uh, Combustion is covered in chapter 13, and you must have a good understanding of how to balance a reaction and different kind of reaction. Most importantly, what is a theoretical reaction? What is air-fuel ratio? What is excess, deficient air, etc. Two types of reactions are covered by test steps, premixed and non-premixed reactions, where we find the fuel oxidizer and product states and then analyze the device for mass, energy, and entropy equation. Before we go over a few problems, just to remind you that combustion has also been covered in closed specific branch. In other words, this is very similar, both are covered in chapter 13, to the open steady branch. So it'll be good to go over both of them at the same time so that you have a complete understanding of the capabilities of test steps. Just to remind, what do you mean by theoretical reaction? Here, methane is burning with air, and theoretical means carbon goes to carbon dioxide, hydrogen is also fully oxidized to H2O, there is no CO, OH, etc., and there is no leftover methane or leftover oxygen. In other words, there is just the right amount of fuel and air in the mixture. If you go to another animation, here it shows what is air-fuel ratio for a theoretical reaction, and when we have excess air or deficient air, lean or rich combustion can be created by a variable lambda, which will assume different values. Lambda equal 1 or 100% means we have a theoretical reaction, theoretical amount of air. Here is, in this animation, the energy equation is shown for a steady state reactor. In a HT diagram, you can see the inlet state and exit state of the reactant. This is a pre-mixed case, obviously. Here, again, the heating value is explained in terms of methane and in terms of reactants going to products at the same temperature and how much heat can be extracted. That's called the heating value. Similarly, the adiabatic flame temperature can be explained by saying that, look, the enthalpy of the mixture is not changing. What temperature needs to be at the exit for that, so that the system is adiabatic, the reactor is adiabatic, no heat transfer. All the heat release is used to heat up the products to the highest possible temperature, known as adiabatic flame temperature. So let's quickly go over a sample problem. We'll just launch a suitable test step, open system, specific branch, and combustion and chemical equilibriums are here, as opposed to these are the closed system branch. So we go to the open system branch. As you can see, combustion is covered in either premixed configuration or non-premixed configuration. For open steady device, the non-premixed configuration is more common. So we'll go with the ideal gas model, NIG model, and there are already solved examples here. So here is we are in the reaction panel. There we set up the fuel, oxidizer, and products. In other words, set up the reaction. So let's say we are burning methane. We'll go with a very simple reaction, and for oxidizer, we'll just pick, let's say, air. Although we don't need to. If we want a standard reaction, we can just go there and just say theoretical combustion with air and execute that. That will make sure the air is picked up and the reaction is completely balanced. You notice that the air-fuel ratio on the mass basis and mole basis are already calculated and shown. So if we want to know what is the heating value, say per kilomole or per kg, what we need to do is that right now the reaction is based on 275 kg of the reactants and products. That's the mass of methane, oxygen, and nitrogen comes to that. So if you want to find, for instance, heating value of methane per kg, then you want to make sure there's 1 kg methane is flowing. Right now, how much methane is flowing? You'll see the methane flowing is 1 kilomole, in other words, 16 kg. So if we multiply the reaction by 1/16, 1 divided by 16, what happens is that whole reaction gets divided by, 1 divided by 16, then the entire reactions get multiplied so that now we have 1 kg of methane, etc. It's necessary because if you go to the state panel, you'll see you cannot enter the mass flow rate. So you have to set it up in the reaction panel. So let's say we have standard condition, 100 kPa, 300 Kelvin. So this is my fuel state. State 2 is automatically hardwired to oxidizer, and oxidizer also comes at 100 kPa, 300, let's say 300 Kelvin. Notice that fuel mass has been picked up 1 kg per second. Oxidizer mass is 17 kg per second, theoretical air. And for products, again, we'll consider same pressure and same temperature, because we are 298 should be precise temperature, but that's pretty close. You see the product, each component properties have been found and tabulated. In the device panel, so we have right now a non-premixed reaction going on. Here's the reaction chamber. State 1 is fuel. As you can see, fuel got populated. State 2 should be oxidizer. And state 3, I can choose any of the exits as products and leave the other one alone, blocked. So we've set up the reaction chamber, and there is no heat transfer, we know. So, I'm sorry, there is no work transfer, no external work transfer. And therefore, if I just hit the calculate button, it will calculate how much is the heat transfer, which is minus 50135 kilowatt, or so many megawatt, 50 megawatt. So for 1 kg per second of fuel coming in, 50 megawatt of heat is being released. Negative means heat is getting lost. So therefore, the heating value must be 50 million joules per kg for methane. You can go to the property table and look at the chart. You will find this is exactly the precise value of heating value of methane. Now suppose you want to know the adiabatic flame temperature if your methane is burning with theoretical air. In that case, state 3, we don't know the temperature, so calculate without the temperature. And we come to the device panel, and we'll say everything else remaining the same, except the heat transfer this time is 0. So you go back and set it to 0. And now if I calculate and click the super calculate to update all calculations, the state panel must be redone with the temperature found to be 2330. So that is the adiabatic flame temperature for the ideal gas model. Of course, if you use the perfect gas model, this temperature will be a lot higher because Cp and Cv will be assumed constant. Just to go over a couple of other features, for instance, let me super initialize. Suppose methane is burning. You want to set up a reaction, methane burning with not air, let's say 50-50 mixture of oxygen and nitrogen. In that case, we can add 1 kilomole of oxygen and 1 kilomole of nitrogen, and this proportion will be maintained in the oxidizer. So for instance, now if I say a theoretical combustion with user-defined oxidizer and execute that, then this reaction will be based on 50-50 mixture of oxygen and nitrogen, and we could redo the entire calculation. For instance, everything is already set up for calculating the okay, you have to redo the fuel and oxidizer just like before and products and calculate the device panel. I forgot that I super initialized this this step. Otherwise, after resetting the reaction or redoing the reaction, you could simply click super calculate and get done with that. You could change the fuel, set up the reaction, and super calculate and get the adiabatic flame temperature for any different fuel without having to redo all your number entry.